How can you say that these are the charged particles rays?
Because they have mass.
Because they have mass, no?
They behave like magnet.
Okay. Because means when a magnetic field is brought nearer to it, then okay, and magnetic field is brought, then they are deflected, either they are attracted or deflected towards that one. Okay. Okay.
Yes, sir.
So we have discussed this one. Let's start the Rutherford model. And Rutherford model, you have also studied Rutherford model in ninth standard. Do you know Rutherford model, something about Rutherford model?
No, sir.
Okay, let's start with the Rutherford model. Okay. Then we shall be the main model is actually of Bohr model. Okay, so let's first start about this one. If I talk about the anode rays, the anode ray experiment was also done. Okay, anode rays experiment was also done, and to find out the actually what he does, let me show you that what he does to find out the proton, that there is some positively charged. So actually, he made perforated cathode. Perforated cathode means like this is the perforated cathode means which is going to have hole inside it. Okay, hole inside it, and an anode. This is positively charged rod and this is negatively charged rod. Okay, perforated cathode, per perforated cathode. So okay, when electricity or high voltage current at low at means further we are just decreasing the pressure, and when the voltage is high, okay, we not only observed here that the rays are moving from negative terminal to the positive terminal. Some rays are moving from negative terminal to the positive terminal, but there are also some rays which are moving, okay, from positive terminal to negative terminal, from positive terminal to the negative terminal. And when the passes through this one, he make the zinc sulfide screen here, zinc sulfide screen here, and these rays passes through these we can simply say here that these rays passes through these holes, okay, through these holes, and that's why they are called canal rays. Canal means because they are just coming through a perforated anode, so they are also called canal rays. Canal rays. Okay. So when he put out the behavior of this one, that these rays were moving from negative positive terminal to negative terminal. This is negatively charged rod. Moreover, when he bring the like for example, if we bring the positive and the negative and the negatively charged magnetic field here, then these rays moves toward the then these rays start moving towards the negatively charged rod. Okay. So let me show you with the help of diagrams and video so that you can understand more betterly. This is negatively charged rod and they started moving from towards the negatively charged because they are positively charged. So they move towards negative. And if we bring the magnetic poles here, okay, if we bring the magnets, North Pole and South Pole, then these start moving towards the South Pole, opposite to that of cathode rays. Cathode rays move toward North Pole, they start moving towards South Pole. Okay, so they were doing, and they were also having positive charge. The difference between this one is that these canal rays depends on the nature of the gas taken in that tube. Okay, these rays these rays depends on the nature of the gas taken in the discharge tube. Discharge tube. Okay, understood? Okay,
Yes, sir.
and nature of electrodes also, and nature of electrode also. So you need to understood this one more betterly. Now moving to the next part here is that, okay, so anode rays and canode ray is, if it is being asked that what is the difference, that uh, all the properties are almost same, that they deflected towards the means they are deflected in the negative field, magnetic field, they are also deflected. Means cathode rays are deflected in the magnetic field, these are also deflected in the magnetic field. Cathode rays means are diverted when electrostatic field or electrostatic force, or when a medium of means when an electric field is applied, then they move towards the negatively charged rod or negatively charged plate. Okay, so similarly, so let me show you the video for this one, then you can understand it more totally. Okay, just a minute.
Canal rays. Let us look at Goldstein's experiment setup. Goldstein used a discharge tube like that of Thomson, with an anode and a perforated cathode in the middle. He also used a fluorescent screen at the other end to sense the rays. At the pressure of about 1 millimeter mercury, there were cathode rays from the cathode towards the anode. Behind the cathode, we also observed a luminous stream of particles proceeding in the opposite direction of cathode rays. Goldstein called them canal rays as they passed through canal-like holes and came out on the other side.
Okay, the same type of experiment was done by various scientists. We can consider this one. Okay.
Evidence for the existence of positively charged massive particles, known as protons, came also from experiments with modified cathode ray tubes. The perforated cathode was placed in the middle, and a plain anode at one end of the tube. The tube was filled with hydrogen gas at very low pressure. When a high voltage was applied to the electrodes, electrons flowing from the cathode to the anode collided with hydrogen atoms, knocking off the electrons from them. The resulting positively charged nuclei of hydrogen, which are simply protons, were attracted towards the cathode, passed through the perforations, and were detected at the other end of the tube as so-called canal rays. In this way, the next fundamental elementary particle, the proton, was discovered.
So this is the way how electron or proton was discovered actually. Okay, now you understood more betterly.
Yes, sir.
Okay, now we shall be moving after these subatomic particle, electron, proton, and neutron was discovered. There was several theories. That means the scientists start giving the theories that there are some particles, and how these atoms and proton, how these electron and protons are arranged in the atoms. Okay, so let's study some theories also and some model also. So most important is the Rutherford model, that we have Rutherford alpha scattering experiment. Okay, Rutherford alpha scattering experiment. And what actually happens in Rutherford alpha scattering experiment, if I talk about. So Rutherford did an alpha particle experiment, and what he does actually, he took the atoms, okay, and he find that uh, gold, actually he made a gold foil experiment. So this is an atoms of gold, okay, this is an atom of gold which is going to have positively charged at the center, and alpha particle is actually is actually helium nucleus. The helium nucleus is actually two positive, because helium has two electron. Okay, when it loses two electron, then it will become helium nucleus only, and it is going to have four atomic number 2 and mass as 4. So this is alpha particle, and it is very small in size. It is alpha particle. It is very small in size. So when we bombard the alpha particles to this gold foil experiment, or to the gold foil, then these most of the alpha particles passes through these gold foils undeflectedly. Okay, most of the alpha particle passes through this gold foil undeflectedly. Some of the alpha particles got deflected at small angles. Some of the alpha particle got deflected at small angles. Okay, at small angles. And a very few alpha particles when goes and come back to its original path. Means they moves and come back to its original path. So this was the observation that alpha particles, because gold atoms is much bigger than the helium or alpha particles. So alpha particle can penetrate through gold atoms. Okay. So he find that most of the alpha particle passes through the gold foil. Okay. Undeflectedly. Some of the alpha particles deflect at small angles, and some of a very few, means approximate 1 in 12, 1 in 20,000s, 1 in 20,000s. Okay, rebound back to its original path. Rebound back to its original path. Okay, you understood?
Yes, sir.
So, what was the observation that most of the alpha particles here? Note down the most of the alpha particles without any deflection show most of the part of the atoms is empty. Means if the alpha particles move without any deflection, so what does it mean? It means that most of the alpha particles are there is a lot of empty space in the atoms. Okay. Okay, out of 20,000, one alpha particles deflected back to its original path. So what does it mean? It means that there is something dense and hard things present in the center of the atom through which alpha particles cannot penetrate. Okay, and there is something very dense and hard present in the atoms through which alpha particles cannot penetrate. Okay. So what was the
Yes.
observation and conclusions here? So write down the observation and conclusions. Observation and conclusions. First one is most of the alpha particles passed without any deflection. It shows that that most of the space in atom is empty. Note it down. Second, out of 20,000, out of 20,000 alpha particles, only one particle rebound back its original path. Okay, out of 20,000 alpha particle, only one alpha particle rebound back to its original path. Okay, it means that there is something very dense and hard substance present in the atom through which alpha particles cannot penetrate. Okay. Okay. So
Yes,
this
sir.
means it is concluded that the positively charged center of the atoms, okay, is not uniformly, or we can say that it is concentrated there. Okay. Understood?
Yes, sir.
So what does it means? That there is something, that there is something very dense and hard present in the atom through which alpha particles can't penetrate. Okay. Understood?
Yes, sir.
And he named it, as nucleus. As nucleus. Okay. He named it 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 as nucleus. Okay. He na Okay, and he called that it is the part where the atoms are going to revolve. Okay,
Yes.
and the next observation was this one. Okay, what was the next observation? The next observation was that actually some of the alpha particles moves or deflected at small angle, means there is some charge particle present in the atom through which alpha particles get deflected. Okay, because alpha particles are already positively charged. So if it is something is positively charged, so if electrons are there, so it will be attracted towards the electrons. And if it is some positively charged nucleus, then it will be deflected towards the nucleus. Okay, so we will say that if there is some means if we the last observation for this one, that some alpha particles deflected at small angle indicate that there is some charged particles present in the atom. Okay, understood?
Yes, sir.
Okay, just a minute. Next is now we shall be moving towards the next one, is that electrons. Now he gives some laws, and there was some drawback of this one. And drawback, we will discuss this one later. What are the drawbacks of Rutherford model? Actually, this is not being asked so much in the examination, so we are not just going to discuss this one much in detail. But he gives some laws, and what he said that atoms, when he gave the structure on the basis of this one, he said that there is positively charged nucleus present at the center, and atoms revolves around it. Electrons revolve around it, and the electrons revolve around it. Then according to the Maxwell theory, okay, when a charged particle revolve around another charged particle, then an electron will collapse, will keep losing its energy and will collapse with the nucleus. And this is make atoms highly unstable, which is not possible. Okay, which is not possible in reality. Okay, so he said that what he actually said in his structure. So structure given by given by Rutherford. What he said actually, he said that the positively charged nucleus at the center of atoms and electrons revolve around it. Okay, got it?
Yes, sir.
Understood? Electron revolve around it. So this was the observation that actually he gave it according to this one. And there were some drawbacks that he was not able to explain, that what if the electrons are revolving, they will lose their energy, and if they lose their energy, they will collapse into the nucleus. So where does the electron goes? Okay, so this was not given by this one. Okay, got it?
Yes, sir.
Next is distance of closest approach. If I talk about the kinetic energy, and let's have some questions here on the basis of this one. Alpha particles accelerated with momentum p, okay, towards nucleus. Towards the nucleus. Then distance of closest approach is R1 if accelerated with momentum 2p towards the same nucleus, then the distance of closest approach, note it down, closest approach will be, okay, will be. So actually what is closest of approach? It is the distance, we can say that if the alpha particle is moving towards the nucleus, then some distance where it can actually, we know that atoms cannot touch each other, okay. Two atoms cannot touch each other. Why? Because of the repulsion between them, okay. So there is something that an atoms can reach to the closest past, and we call it distance of closest approach, okay. Have you noted this one? Question?
Yes, sir.
Okay. So what is the distance of closest approach? Let me explain you. That if this is a suppose alpha particles, okay, this is an alpha particles, and this is the nucleus, positively charged nucleus of the atom, okay. And whatever the charge of this one in this nucleus is equals to the atomic number of this one. For example, if this is the helium or gold atoms or whatever, the number of proton present in this nucleus will be equal to the atomic number. Okay, got it? The total charge will be equals to number of Z is the atomic number, we represented by atomic number, and Q is the charge of an electron in positive. This will be considered as Q2. This is the total charge, and this is the Q1 is the actually alpha particle which is going to have +2 charge. Okay, got it?
Yes, sir.
Now this is moving towards this one. This is moving towards this nucleus. Okay, and we know that if B is a point here, okay, this is A and this is a B point, and let the distance between this one is R1. R1 is the field where the this will start exerting, this alpha particles will start, or we can consider that it's closest approach. Okay, so here if I talk about this one, that the kinetic energy of this alpha particle will be equals to half mv square. Okay, understood? Kinetic
Yes,
energy
sir.
alpha particle is equals to half mv square, and energy has another formula also, that is q into v, qv. Okay, this is another formula, that is the charge into v. This is another formula for the energy of the electrons. And how can you understood this one? That you can understood v is equals to w upon q. You understood? Define 1 volt in the physics. The work done in moving 1 coulomb charge from infinity to a point in electric field is known as 1 volt. So V, and you know, work done is also known as energy, because work done energy has same joules, same unit. Okay. So when you multiply this one, these two, what you will get? V into Q is equals to W. Got it? And
Yes,
what
sir.
is V? V is V and Q is the charge. So this kinetic energy is also equals to work done, and that would be also equals to QV. Got it?
Yes, sir.
Got it? And let's suppose this distance at B point here, and this we have C point here. Okay. And let's if I'm talking about here, at B point, it will be going to have some kinetic energy as well as some potential energy. Because when the alpha particles start moving, and it will start coming and come closer to each other. Okay, so there will be a repulsion force will start coming here. Okay, got it? Let the alpha particles reaches to this distance, otherwise it will not be able to penetrate. Okay, so we will say that it at this C point, okay, at this C point, it will not be able to move further. It will be the bond back because of this positively charged force of this nucleus. Okay, so let this point is actually C point, where the kinetic energy will become zero. Kinetic energy will become zero, and all the energy will be. Why kinetic energy will become zero? Because velocity will be zero, because it is not moving further. It comes and stop here and then start moving back. So here the maximum potential energy will be, means all energy will be potential energy. You understood? Understood?
Yes, sir.
So here it is moving, it is not having any potential energy because it start moving here. So it is going to have only kinetic energy. At this point B, it is going to have kinetic energy and some potential energy because the resistance start forcing here. Okay. And at point C, we will find that there is no kinetic as well as, means there is no kinetic energy, only potential energy is there. Why? Because it gets stopped here. Okay. Now from the law of conservation of energy, law of conservation of energy, law of conservation of energy, you know that the total energy at every point remain constant. In total energy, or we can write total energy at every point. Total energy at every point. At every point means we can say that at point A will be equals to total energy at point B will be equals to total energy at point C. Okay, got it?
Yes,
Got
sir.
it? Similarly, we can say that total energy at point A will be equals to total energy at point C. Got it? Got it?
Yes, sir.
Now, what is the total energy at point A? Total energy at point A will be QV. That is equals to Q into V, means charge. What is the value of this charge and what is its potential difference? Okay. And that would be equals to, there has a formula of between, and there is also a energy, or we can say that there is also formula between the two, one that is K bracket Q1 into Q2 upon R. R is the minimum distance. Okay. So this is the formula for calculating the minimum distance, where R is the minimum distance. So we'll take that minimum distance. Okay. Q1 is the charge of this one. Q2 is the charge of this nucleus into R minimum. Okay. Got it?
Yes, sir.
Now, if you are not getting this one, then let me explain you one more time and you get familiar by solving this type of question. You need to just note down the formula and keep memorizing, because we are not going to, in exam, we are not going to have the derivation of this one. They will only ask you the question that in this way. Alpha particle accelerated from momentum this. So we will going to solve this one. First, have you noted this one?
Yes, sir.
Now moving to the next part here is, now we know that total energy at point B will be equals to total energy at point C. See, here we have find out total energy at point A is equals to total energy at point C. Okay, we have just equated these two and we have made this formula that QV, the energy of this one, is also equals to total energy of this one. Okay, so that is we have written this one, that is the K into K is constant here, Q1 Q2 upon R minimum. Okay, got it? Or are you not getting clear this with me? Should I move forward?
Yes, sir.
Now kinetic energy plus potential energy will be equals to total potential energy at point C. This we are talking about B, because at B it is going to have some potential energy as well as some kinetic energy, and at point C it is not going to have any kinetic energy. It is going to have only potential energy because it is not moving at point C. So what is the kinetic energy at point B? So kinetic energy at point B will be half m v1 square if it is moving at velocity v1. And what is the energy at point 2? That will be q1 q2 upon r1. R1, what is r1? R1 is the distance here. What is the distance here? Okay, this is the distance r1. Got it? R1 is the distance between B point to C point is known as the R1 distance. Distance between noting this one. Moving further, we'll have this one is the energy of this one. Now the total energy of this one will be K into Q1 into Q2. This is the point C energy. This is the R minimum. minimum. Here the distance between the particle has reached this one, the particle has reached this one, then this R minimum is this is the R minimum distance. Now at point B, we are just talking about B and C point, so this is the R1 distance here. R1 distance here. So when we do the question 2 or 3 question 2 regarding to this one, then it will be more clear about this one. Okay. So this is the formula. This is the formula that we have to put. Now we shall be moving towards the question. What was the question? Have you note this formula that at point B will be half m. What is the velocity of this one? It is if it is moving. Okay. Got it?
Yes, sir.
And k is equals to q1 q2 upon r square, and the k is equals to q1 into q2 upon r minimum. So please note it down, then we shall be moving towards the question. What was the question? What was the question? That alpha particle, read the question please.
Alpha particle accelerated with momentum p towards nucleus. Then distance of closest approach is r1f accelerated with momentum 2p toward the same nucleus. Then the distance of the closer approach will be.
Here it is that alpha particle is accelerated with momentum p. Okay, towards the nucleus. So here momentum is being given to you, that is p. Okay, and momentum formula is m into v. Got it? Now next is that momentum towards the nucleus, and the distance between the closest approach is r1. And the distance between the closest approach is r1. If it is accelerated with momentum 2p, means twice, means the momentum is doubled, then towards the same nucleus, then the distance of closest approach will be. So you know that we have the kinetic energy half m v square is equals to, this is the formula at point A. Okay, this is the formula, and this is the k q1 q2 upon r minimum. R minimum. This is the formula. Okay, got it?
Yes, sir.
Now, if we are just considering this one, that momentum, if I put this value in terms of momentums, so how can I write this one? You know that half m v square, just if I'm just writing this one, so you can take half. Okay, got it? And m into v is momentum, so you can write p into v by 2. Okay, and you are just going to have this one like the current, right, like this one. Can you write this like this one? Tell me.
Yes, yes, sir.
Okay. So if I square this one, or if I divide it, if I multiply m here one more and m here one more. Okay. So what you can means I'm just multiplying m on both sides. I'm just multiplying m on both sides. So what you can write here is, this is mv into another mv, okay, upon m. You can write it like this way.
Yes, sir.
So what you can write, if this is the formula for kinetic energy, so the same formula for kinetic energy in term of momentum can be written like this: half 1 mv into another mv upon m. Got it? Is equals
Yes,
to
sir.
k q1 q2 upon, is equals to k q1 q2 upon r minimum. R minimum. This is the closest approach. Okay. Now what you can write here, that this thing momentum is actually, if I ask about you, and if I ask you that all things are constant, charge is constant, the first charge, nucleus, whatever the charge of the particle is, you can consider this term is constant, this term is constant, this is not changing. So we can say that this r minimum, or we can say that p square is directly proportional to r minimum. Sorry, must be proportional to r minimum if I think that all the charges is constant. If everything is constant, except we can say that this p square is, this mass is constant, this is constant, this is not changing, everything is same. Like you read the question here, read the question and just listen to it. Alpha particle accelerated with momentum p, okay, towards the nucleus, So then the distance of closest approach r1, and the distance of closer approach is actually r1 here. If it is accelerated with the momentum 2p, means the momentum has become kitna double towards the same nucleus. So whatever the charge of the nucleus is, we don't know whatever that, but whatever the charge it is going to have q2 value, it is constant. And q1, this is alpha particle. Whatever the charge of alpha particle, it is +2, it is also constant. So q1 and q2 is constant, but the momentum has changed. And the mass is also constant. Only the velocity is changed. That's why, because momentum is p is equals to m into v, and alpha particle's mass is not going to change. Only the velocity is going to change here. Okay. So if I explain you the same one here like this way, you can see here that the formula for this one is in terms of momentum for the closest approach. Okay. That is p square half p square by m is equals to half p square by m is equals to half q1 q2 by r minimum. Okay. So if I talk to you this one, that m of alpha particle is not going to change. The q1 is the charge of alpha particle, it is not going to change. Here q2 is the nucleus towards it which the electron is approaching. Okay, sorry, proton alpha particle is approaching. So this nucleus is also changed. So we can say that constant term, if I remove the constant term, half is also constant, half is not going to change. So we can say there the p square is inversely proportional to r minimum. Okay. So it is asking about the distance of closest approach. So we can write here that if I'm saying p square is inversely proportional to r minimum, then I can write here that r minimum is inversely proportional to p square. Got it?
Yes, sir.
Now, if I'm talking about this one, that this is 1, okay, and if I write it like this way, and this p square, okay, p square. Now it is saying that p square has become double, okay. So we'll take here that r minimum dash will be equals to, now the p has become double, now 2 times of p. So you will write it like this way. So this will become 4p square, and actually this is the original one. So you can write there r minimum for the next time will be r minimum will be 1 by 4 times the original. Okay, means simple word that if you are just increasing the momentum double, if you are just doubling your momentum, then the electron or the alpha particle will come 4 times closer to the nucleus. Okay, a distance will become 1/4 of the original. So first of, if it is reaching, suppose this distance, this is 4, let this one is 4 nanometer. Okay, then it will now if you have doubled its momentum, then it will become 1/4, means it will reach to distance of 1 nanometer. Okay, got it?
Yes, sir.
So this is the question. Then let's do one more question regarding to this one, and we shall be moving to it. This is important topic. Okay, most of the students. So note it down. An alpha particles accelerated towards gold nucleus whose atomic number is 79. Okay, with we can say that here the voltage is given to you megavolt with 4 megavolt. Okay, find the initial kinetic energy of the distance of the closest approach. Kinetic energy of the distance of closest approach. Okay, so what is saying? It is an alpha particle, it is attracted toward the nucleus of gold with 4 megavolt, and voltage is given to you 4 megavolt. Okay, so find out the initial kinetic energy and the distance of the closest approach. You need to find out the r minimum. Okay, and initial kinetic energy you need to find out. So which formula you are going to use? Tell me. Kinetic energy is equals to half mv square. It is also equals to QV.
Yes, sir.
So Q, what is the value of Q? What is the value of Q of alpha particles? Alpha particle has 2 positive charge. Okay, it is, I've told you that it is doubly charged helium. Okay, so this is 2. Keep in mind that alpha particle has positive 2 charge. So it will not be given to you in examination. You need to find out, means you need to memorize this one, that alpha particle has double 2 charge. Okay, and what is the voltage given to you? What is
4
the voltage given
megawatt.
to you?
4 megawatt.
Yes. So actual charge of this one is 2, but what is 2? 2 in the form of, means we need to write it in the form of electron charge. Okay, so actual charges means 2 times of electron charge. Okay, 2 times of this charge is N into E. Okay, so N is 2 for this one because it has loosened 2 electrons, and E is 1.6 into 10 to the power minus 19 coulomb. Okay, this is the charge of an electron. So total charge, if I talk about the total value of this one, Q is equals to N into E. The total charge is equals to N is the number of charge that is going to have, or number of electron that is loosened, and E is the electron charge. So we'll write 1.6 into 10 to the power minus 19 coulomb. Okay, got it? And then
Yes, sir.
mega means 4 into 10 to the power 6, positive 6. Okay, mega. Got it?
Yes, sir.
Now, what value you will get? You are going to get here? Tell me. Multiply this one and get the value. 3.2 into 4 into the power will be 10 to the power minus 13. Then you multiply this one.
12.8.
What is?
12.8 into 10 raised to minus 13.
Yes. So when you write it in standard term, we'll get 1.28 into 10 to the power minus 12. Got it? Noah, are you getting this one? Means, do you think that it is difficult for you? Are you getting this one, or is it these questions are okay? You are getting this one.
This particular question is a little difficult.
This particular questions. Actually, this is, we are just studying that there's some closest approach. For example, when the alpha particle is moving toward the nucleus, okay, so towards the gold foil or something, then there is a value, or there is a level up to which then alpha particle can reach toward the nucleus of the, towards the nucleus of the gold atoms, gold nucleus. Okay, so if the alpha particle is bombarded towards the nucleus, then it is a limit where up to which it can go and rebond back. It cannot penetrate towards this, okay, this positively charged nucleus. So that is called minimum, or we can say the closest approach, that how closest an atom, or sorry, an alpha particle can reach to the nucleus. Okay, got it? So let's have one more question, then you will be able to understand this one. Let's start one more. Okay, don't worry. If a proton is moving with a velocity, with the same speed used in alpha scattering experiment, okay, if only the question from the Rutherford models only comes from this portion, closest approach, okay, and sometimes the drawback is being asked. So it is a question, if the proton moving with same speed, used in alpha scattering experiment, alpha scattering experiment, okay, then the distance of the closest approach, then the distance of closest approach becomes how many times? Becomes how many times? If the proton, now it is proton, okay? And what he said, what he take in alpha accelerating experiment, he take alpha particles. The proton is going to have the charge difference we are just having, okay? Alpha particle has charge that is 2e and proton has charge only 1e. So it is indirectly saying that if a proton is moving means if a particle which is going to have half the charge of alpha particles is moving with the same speed, then the closest approach. So tell me, will it move more closer to it or away from it? Tell me, will it move more closer? So let's check. Let's check. Okay. Now you understood the question. What is the difference in what we are just having? Okay. Do you understood this question or should I explain you one more time? No, huh?
Understood.
You understood this? So it is saying that instead of using alpha particles, if we are just having only proton and if it is moving with the same speed as in alpha scattering experiment, so what is the closer approach and how many times it become closer to it or what is the distance? Means we need to find out. Okay. So we know that half mv square is the kinetic energy of the proton, whatever it is going to have. Okay. This is the proton, the mass of proton we are just going to have, and this is the velocity of this one. Okay. And that is equals to k q1 q2 upon r minimum. This is the, because it is asking for the closest approach, so we are just going to put this value k q1 q2 upon r minimum. Okay. Okay. And here r minimum for the proton we are talking about. Okay. Got it? And if I talk
Yes, sir.
to this in half m, this is the mass of alpha particle into velocity is same for both because it's saying same velocity. So I'm not writing here proton velocities because the velocity is same. Okay. Now k is constant. It is also same. Q1 here, Q1 is the charge. We can take charge of proton here because Q1 is the charge of proton. Here we are taking charge of alpha particles. Okay. Charge of alpha particles into Q2 is the same gold nucleus. So Q2 is not going to change. So we are right. Q2 is same both for both the cases. Okay. And we need to find out the ratio for R minimum. And here is the R minimum for alpha particle. Alpha particle. Okay. Now we are just dividing the first equation by second. Okay. This is the first equation. Second equation. Dividing the first equation by, or we can divide the second equation by dividing equation second by first. Okay. What you will get here? We'll get here this half and half will get cancelled out. This v square will get cancelled out when you put this two one over the other. Okay. And then you will take mass of alpha particle upon mass of proton. Got it?
Yes,
Got
sir.
it? This k and k will get cancelled out. This q2 and q2 will get cancelled out. Okay. So you will find here that you will write q alpha particle upon r minimum for alpha particle is being divided by, means this portion is being divided by this q for proton upon r minimum for proton. You understood this one?
Yes, sir.
Okay. Now tell me what's the ratio of r minimum of proton to tell me. Other things are going to they are cancel out each other. So tell me, try to find out, okay, by your own. Then I'm going to help you. Mass of alpha particle, I'm just going to write that in terms of proton, mass of alpha particle is 4 times. If mass of proton is 1, then alpha particle is going to have 4 mass. Helium has four mass, proton has only 1 mass. So you can write it like this way, and the mass of charge of alpha particle is actually 2 times the charge of proton. So do it, try to find out what's the ratio. Then I'm going to help you. Tell me. You will write like this: 4 by 1 is equals to Q alpha is 2 into E upon R minimum for alpha particles into I'm just reciprocating this one, okay? Because I've just changed the division sign. So I'm just reciprocating this one. So this will be R minimum for proton upon Q of proton. Q of proton is actually N into E, 1 times 1 into E, charge of proton. Okay, so E will get cancelled out. Okay, now this will also get cancelled out. 2 ones are 2. Okay, now we are just going to have like this: 2 is equals to R minimum for proton upon R minimum for alpha particles. Okay, now this will goes to this time. You will get R minimum for proton will be 2 times of R minimum for alpha particles. R minimum 2 times of R minimum for alpha particles is equals to R minimum for proton. Understood?
Yes, sir.
Is there any doubt?
No, sir.
Closest approach. What if the same question, if I give you the same question, but if I instead of using the same speed, I'm saying that a proton is moving with same potential, same electric potential, means same voltage. Okay, then what would be the ratio? So if I instead of giving you that if alpha particles and proton accelerated through the same potential, if the alpha particle and alpha particles and a proton accelerated through same potential, same potential. Okay, then what is the ratio of R minimum to R, means R minimum for proton to R minimum to alpha particles? What is the ratio? So which formula you are going to use here? Same potential, they are moving. What is potential? V is equals to W by Q, work done per unit charge. Okay.
Yes, sir.
Okay. So you need to keep in mind when we are just having alpha particles and the proton which are accelerating with the same potential. Okay, so you can write it like this way, that QV, instead of using kinetic energy formula equating with K is equals to Q1 Q2 upon R minimum. Okay, if for example V is same here. Okay, and Q1 is like this is proton, this is also proton. Got it?
Yes, sir.
Got it? And now for this one, Q alpha into V is equals to K Q alpha into Q2 upon R minimum. Okay, got it? Now saying same
Yes.
potential, so this will cancel out each other. Got it? And here, this will also be going to cancel out. This will also be going to cancel out each other. Now this is 1 upon 1. When you divide it like this way, K will also cancel out each other. And Q2 will also cancel out each other. Got it? So what you will write here? Minimum for proton upon alpha particles. So actually this is a ratio because the ratio is 1 here. So if you write it like this way, 1 upon R minimum for alpha particle upon 1 upon R minimum for proton. So this will be again going to, like, you will reciprocal this one, you will write it like this way: R minimum for alpha particles upon R minimum for proton will be equals to 1 upon 1. So ratio will be 1. Okay. So if they are moving with same potential, alpha particles are moving with same potential, okay, then their ratio will be 1:1. Okay. But if I'm talking about the proton and alpha particles are accelerated with same speed, then their means we can say that the closest approach distance will be 2 times. Proton closest approach will be 2 times. Okay.
Yes, sir.
Then the alpha particles. So now you a little bit, if you got understood this one, it's okay. We will discuss the question regarding to this topic same in other classes. So because there are some topic that we actually study for the first time. And if we study for the first time, then the brain does not trigger this one because these are the topic that you have never studied before since you have started studying. Okay. So that's why some of the topics which we are just studying for the first time, the brain does not allow to, I mean, it create a resistance to accept those things. Okay. The things that we have already studied, we are just practicing something. For example, if I started teaching you in Chinese language, which you have never, so your brain will start means rejecting that. You will not try to focus. Okay, you will like to watch the movies in your own language in which you are very much comfortable. Okay, but if the language is different and you need to read the subtitles only, then you will probably skip that movies. Okay, because this will not trigger in you. This will not brain will not allow to enter those things, those new things into or different language in which you are just going to have much effort. Okay, you are just reading the subtitle and then you are understanding what it's saying. So it will just create a problem for you if you are not habitual of doing that. Okay, the same thing is for the studies or a topic that we are not studying for the first. We have not studied earlier in any other classes that you have studied till yet. So in those cases, if we are studying such topic, then which you are not here studied before, then those topic actually create a resistance and the brain uh, hit it. We can say that if we are so what are the how can we study such topic? This is simple that we study today and we do 1 or 2 classes for the same topic, for means we study further and then we'll take the revision portion from this one and we will do some more question from this one and you will be able to understand this one. Okay, you understood what I'm saying?
Yes.
Okay, let's move further. Now, what are the limitation of Rutherford models? What are the limitations? Limitations of Rutherford model. I have already told you that in the Rutherford model, there was a limitation that he said that electrons revolve around the nucleus. But according to the Maxwell theory, if the charged particle revolve around uncharged or other charged particle, then due to attraction, it will keep on losing its we can simply say here that it will keep on losing its energy and that will finally collapse into the nucleus. Okay, you understood?
Yes, sir.
Okay, so here we have first of all that unable to explain the stability means stability of its nucleus, unable to explain the stability of nucleus. Second, what does it does? According to Maxwell, Maxwell, if a charge particle revolve around another charge particle, another charge particle, then it continuously radiates its energy, radiate or release its energy. Okay, it continuously radiate or release energy. Got it? And because electron is not going to have much energy, so for an electron, it will take how much time? 10 raised to the power minus 7 seconds. This is very, very small time for an electron to collapse with the nucleus. So for an electron, it will take approximately 10 raised to the power minus 7 seconds to collapse with the nucleus. Okay, to collapse with the nucleus. With the nucleus. Okay. And
Yes.
there was a spectrum theory that when the electrons, that means if it is losing continuously, if it lose continuously energy, Okay, then it will gives you that will going to study the spectrum that it will give you continuous spectrum that you have not studied here. So I'm just going to write that drawback, but I will explain you when I will teach you the spectrum, continuous spectrum. Okay, so actually when the energy is being released by the electrons in case of hydrogens, so it does not, it shows discontinuous spectrum, but actually it must show continuous spectrum. So this is the results. Okay, so that's spectrum portion we're going to study when we'll learn spectrum. Okay, so atomic spectrum spectrum not explained by the not explained by Rutherford. Okay, next one is Planck's quantum theory. So next one is, have you noted this one?
Yes, sir.
Next one is Planck's quantum theory. Planck's quantum theory. Quantum theory. According to the Planck's quantum theory, means an electron absorbs or emits energy in the form of quantum. Means an electrons either absorb energy or release energy in the form of quantum or the packets, energy packets. We called it photon. Okay, and photons or the quantum show, we can say that they show dual nature. One is particle nature, another one is wave nature. Okay, so what actually we can simply say here is that according to the Planck's quantum theory, what he said that whenever an electron is absorbing the light or energy, then it absorbs the energy in the form of discrete packets or the packets. Okay, like we can say that this is not absorbing the energy like in a continuous manner. Okay, it absorbs the energy in discontinuous manner in the form of packets, energy packets. Okay, so here you have to write that electrons absorb or emits energy in the form of quantums or photons okay, and photons, next one, photons or quantum show dual nature, it shows dual nature. Okay, one is wave nature, one is particle nature, and another one is wave nature. One is particle nature, and another is wave nature. Another is wave nature. Okay, note it down, please. Done? Done? Noted? So he said
Yes,
that
sir.
this energy is given by h nu. Okay, h nu. Okay, or where h is the Planck's constant. Okay, where here h is Planck's constant, and it can be nu. Nu is the frequency of the wave we are talking about. So energy in the form of waves can be written like E is equals to h nu. H and nu is also frequency. Frequency is equals to we can simply define frequency by c by lambda. C by lambda, where c is the speed of light, and lambda is the wavelength. Okay, so in terms of, if I talk about the wave nature, so energy can be predicted of this wave by using this formula or by c hc lambda. Okay, where we can say that h is Planck's constant. Okay, which has a value of 6.6 into 10 raised to the power minus 34 joules per second. Joule seconds. Okay, note it down, please. And if I talk about this same energy for in terms of dual nature particle nature, so it is given by E is equals to mc square. M is the mass of the particle and v is the velocity of the particle. Velocity of the particle. So we don't study E is equals to mc square in our syllabus generally. We just study the wave nature of this photon. Okay. Okay.
Yes, sir.
So noted this one.
Yes.
Next. Next, if I talk about this one, that the same energy in joules, electron volt, sometimes the energy is being asked in joules, sometimes the energy is being asked in electrons volts. Okay. Sometimes the energy is being asked in different forms. So there is a formula for each of them. Okay, for the convergence. So if we have simple one, E is equals to h nu. Nu is the frequency of the wave. Okay, this is the simple formula, and it is given in the joule. Means the energy will be, you will get in the form of joule. Okay, for example, and E is equals to h. We can write it h c lambda. Okay, where h is 6.6 into 10 to the power minus 34 into c is the speed of light 3 into 10 to the power 8 upon lambda is the wavelength. Okay, in angstrom. So generally the unit for this one is meter. Wavelength unit is meter. But you know that if we are just converting, we generally have the wavelength in our numerical problems. So we have wavelength in the angstrom. Okay, so if it is in angstrom, then we will generally have this value, that 1 angstrom is equals to 10 to the power minus 10 meters. So we can write it, it is in angstrom, but we have to multiply it by 10 to the power minus 10 meter. So actually what we are just going to have here is that, okay, okay, this is the value when you need to find out the energy in terms of joule, 2 into 10 to the power minus 15 upon wavelength. Okay, if the wavelength is only given to you. Okay, are you getting? This is the shortcut formula that you have to remember. And if it is given in the electron volt, then the same will be 10 raised to the power 12400, and where the wavelength will be in angstrom. Okay, got it? No, got
Yes,
it?
sir.
Okay.
Yes.
And similarly, sometimes the energy is being asked in the electron volt, sometimes the energy is being asked in the joules. Okay, so you have to write the different formulas. But actual formula is this: E is equals to h nu and sc by lambda. Got it? And here's the one more formula for E dash, means energy is equals to number of photons. So if, for example, we have, this is the energy of one photon, and if sometime the 500 photons are passing, then E to total energy, E total will be equals to number of photon into energy of one photon. So it is number of photon into energy of one photon, energy of one photon. So sometimes it is being like this way. Okay, done this
Sir.
one. There can be so many questions in your NCRT that is being asked on this Planck's quantum theory, and you have to do those questions by own. Which this is very simple, but we are just going to have some questions for you. Okay, got it?
Yes, sir.
So here we are going to have this one. Question is, for a photon, for a photon of wave number wave number is equals to 10 raised to the power minus of 10 centimeter inverse. Wave number is actually equals to 1 by lambda. Okay, got it? Got it? Wave number is 1 by lambda. Wave number is equals to 1 by lambda. So sometimes a wave number is given to you. Okay, so reciprocal of wavelength is called wave number. Okay, got it? So it is given to
Yes.
you that the wave number is 10 to the power minus 10 second inverse. Okay, find the energy in joules per photons. Okay, electron volt, second kilojoule, okay, and kilocalorie per mole. Kilocalorie per mole. So joules per photons means per photon means simple. We need to find out for the one photons. Per photons means we need to indirectly it is being asked that you need to find out the energy in joules. Okay, so you know this one E is equals to h c lambda. Okay, h c lambda. But we can write it like this way: h c into 1 by lambda, and 1 by lambda is wave number. Okay, got it?
Yes, sir.
So what you will write here, lambda's value is 6.6 into 10 to the power minus 34 into c is 10 to the power 8 into this one is, what's the value here? Lambda is 1 by lambda is 10 to the power minus, actually this is 10 centimeter inverse, and we have to convert it into meters. Okay, because the standard unit should be in meters. So how can we convert this one into meters? Tell me. If I convert it into meters, so we can say that 10 is equals to 1 by wavelength. Okay, 10 centimeter inverse. Okay, are you getting this one?
Yes,
Something
sir.
is going to happen. What is the wavelength of this one? If 1 by lambda is equals to 10, okay, then the value of 10 is, then the value of 10 centimeters. Okay, 10 centimeter inverse, or we can say it is a unit 10 10 this one. Okay, so what is the value of wavelength? Wavelength will be equals to 1 by 10, 0.1, and 0.1 if you write it into in terms of meters, then it will become 10 to the power minus positive 3. Okay, got it?
Yes, sir.
Calculate this one, get the value. Note it down that wave number, this is represented by this one, 10 centimeter inverse is equals to 10 to the power 3 meter inverse.
A 19.8 into 10 raised to minus 23.